Okay, right now I'd like to kick things off by providing all of our listeners with some background information on Scheugenpflug and explaining why this particular webinar will be different than some others that you might have attended. So let's get started. Scheugenpflug began in 1990 as a project at Siemens to improve automated dispensing. Now, since then, we've grown into a leading manufacturer of adhesive bonding, dispensing, and potting systems, and are recognized throughout the industry for our expertise in dispensing highly viscous and abrasive materials. Today, Scheugenpflug has more than 470 employees and operates multiple subsidiaries across the globe. Roughly 80% of our business focuses on automotive and aerospace applications. So I'm sure most of you have attended webinars in the past where the presenter has in one way or another tried to get you to purchase a specific product or solution. Well, that's not what we plan on doing here. This webinar is educational. The objective is to help you increase manufacturing throughput and improve dispensing yield by reducing filler damage, specifically microsphere breakage, and maintaining material quality. Specific topics that will be discussed include the overall role that yield costs plays in achieving the lowest possible cost per part produced, critical factors that contribute to adhesive dispensing yield and associated costs, common dispensing challenges when using material fillers, and factors that impact microsphere breakage, and finally, important considerations when specifying an adhesive dispensing solution for highly viscous and/or abrasive materials. Okay, first things first. Before we get into the meat of this webinar, it's important to provide everyone with some high-level background information on the adhesive dispensing market. We've got a couple different statistics up on the screen courtesy of Grandview Research that provide a bit of context as to just how rapidly the fluid dispensing market is growing. According to Grandview, the dispensing equipment sector alone will eclipse $10 billion over the next 6 years, with revenue exceeding $3.4 billion. Primary drivers of this growth will include the increasing demand for more accurate and efficient fluid dispensing systems as an alternative to manual application, along with high demand for more exacting fluid formulations across the electronics, construction, medical, and automotive industries, which will be the focus of this webinar. Over the last decade, auto and aerospace manufacturers' drive to enhance efficiency, improve part quality, and reduce costs has increased immensely. Adhesive dispensing systems play a critical role in achieving those goals, and as a result, they have emerged as one of the fastest-growing automation devices in the production environment. Today, dispensing systems can be found at virtually every stage of the assembly process. Specific examples include potting and sealing electronics and other components from moisture and other environmental damage, applying gap fillers, thermally conductive adhesives that draw heat from electronics, insulation and encapsulation of electronic components, transformers, ignition coils, etc. Adhesive bonding using adhesives to form a material bond between two or more assembly parts, and also conformal coating by applying a protective finish to delicate electronic surfaces. Given its increased role in both automotive and aerospace manufacturing operations, properly managing the cost associated with adhesive dispensing has become critical to reducing the overall cost per part produced. Generally speaking, dispensing costs can be separated into 4 separate categories, and they are the initial capital cost of dispensing equipment, operating costs of dispensing equipment, yield costs, or the cost of lost yield, and lastly, waste and repurposing costs. When it comes to selecting a dispensing solution, many manufacturers use initial costs as the primary driver for their purchasing decisions. However, our involvement with over 4,500 projects worldwide reveals that yield costs often make up the dominant fraction of total cost of ownership, or COO as it's sometimes called. This is particularly the case in operations where expensive adhesives are needed to bond dissimilar materials or seal exposed parts, as lost yield and downtime associated with an underperforming system can quickly exceed any initial savings. On this slide, we have a relatively simple equation to demonstrate how important yield costs are in reducing dispensing costs, as well as the overall cost to produce a part. On the top of the equation, we have the initial fixed cost of dispensing systems and ancillary equipment, labor costs, recurring costs, and finally yield costs. Together, these 4 variables make up total dispensing costs. On the bottom of the equation, we have lifetime of dispensing equipment, throughput rate, composite yield, and equipment utilization, which is another way of saying equipment uptime. Plugging in hypothetical values into the equation on the previous slide allows us to compare the cost of ownership, or COO, per part between the two different dispensing systems. In the first column on this slide, we have System A, which has an initial purchase price of $170,000 and a service contract of $21,250. In the second column, we have System B, which has a higher purchase price of $250,000 and a service contract of $31,250. System A has a 20% higher throughput than System B. However, it also exhibits a 1% lower yield. The only other difference between the two systems is the operational lifetime. System A, we are saying, has a lifetime of 3 years, while System B is 4 years. The longer lifetime can be attributed to the use of higher quality electrical and mechanical components, which is reflected in System B's higher purchase price and service contract. So when we plug all of these numbers into our dispensing cost equation, we see that despite the significantly lower purchase price and service contract, along with higher throughput, System B still produces parts that are $3.58 less expensive than System A. Over the total lifetime of the equipment, this translates into over $400,000, which is more than 5 times what the manufacturer initially saved by purchasing the less expensive dispensing system. By diving a bit further into this hypothetical example, we can see how dispensing costs are allocated. In both System A and System B, yield represented the majority of dispensing costs. In the less expensive System A, it was 70% of the total, and in System B, it was 57%. In both cases, the initial cost of purchasing the system made up less than 20% of total costs. The point we're trying to get across here is that when evaluating different dispensing systems, it's important for manufacturers to realize that the combined cost of labor, recurring costs, and the initial purchase price represent only a fraction of the system's cost of ownership. So if we take into account the fact that yield cost is the biggest driver of dispensing system cost of ownership, the question then becomes how we can improve yield in dispensing applications, and more specifically in those where material fillers are utilized. Fillers are used in dispensing applications to achieve a number of desired effects. For example, glass beads are often used as spacers to ensure the minimum bonding material exists to maintain bond strength between dissimilar materials. Engineered fillers can also be used to give the surface certain properties, such as thermal or electrical conductivity. Silica-based products are another commonly used material filler that help to reduce the amount of engineered dispensing medium, which in some instances can be highly cost-prohibitive. Hollow glass microspheres are a particularly important material filler used in applications where minimizing the overall weight of the part being produced is critical. As we will see on the next slide, this is often the case in aviation and aerospace applications. One term that every airline part manufacturer is familiar with is the breakage equation. The breakage equation details the effects of weight change to an aircraft. So in the simple calculation we have on this slide, which was done for an Airbus A320, we can see that over the course of 50,000 trips, a mere 1% reduction in mass will save 3,119 metric tons of fuel. The decreased weight improves fuel efficiency, translating into $1.6 million in savings over the plane's lifespan. Now, when you consider that many airline companies have hundreds of these planes operating in their fleet, we can see just how important it is to keep the weight of parts as low as possible. The use of hollow glass microspheres in dispensed media is one of many different methods that have helped manufacturers achieve component weight reductions by lowering the density of the dispensed medium. When utilizing microspheres as a filler for standard material formulations, one thing that can drastically reduce yield and dramatically inflate overall costs by increasing the number of defective units per shift is breakage. This is largely attributable to the microsphere's thin-shielded, hollow nature, which makes it easy for them to be broken by compression at constraint points, shear under areas of tight clearance, and impact at turns in transfer equipment. Overall, dispensing hollow glass microspheres can be a challenge, particularly when using traditional dispensing machines. In fact, in some applications, a breakage rate of up to 80% can occur. Microsphere burst ratings can vary significantly depending on their specific composition. However, one of the primary contributors to breakage that we at Scheugenpflug see across almost all applications is high-pressure mechanically driven equipment, which can dramatically increase the density of the dispensed media, resulting in costly quality issues. When specifying a dispensing solution, there are many different factors that users have to look at that will impact breakage rate and overall material quality of dispensed media. Some of the primary contributors, which we will discuss on the following slides, include system operating pressure, pump choice, material agitation, material recirculation, seals and surface finishes, and lastly, temperature. One factor that can have a significant impact on microsphere breakage rate is dispensing system operating pressure. Systems that use high pressure to flow material can damage or crush fillers and increase material density. In addition to losing money as a result of the defective part, there are other consequences that filler damage can have on a manufacturer's bottom line, such as higher costs to process the heavier fluid or adhesive. Material under immense pressure will lose homogeneity and fall out of solution, which affects the dispense speed set in automation and the desired material properties. Bonds are broken within the material, causing undesired resulting effects and properties. Now, one solution that can eliminate many of these problems is the use of low-pressure dispensing systems. Low-pressure systems can maintain flow without damaging the material and do so without the need for priming. Now, another added benefit that may or may not directly impact defective parts per shift is system safety. In most cases, fewer safety measures have to be taken with a lower pressure system, which can translate into shorter maintenance periods and less downtime. One additional comment on pressure, though. We should mention the impact of filler separation within the lines, valves, etc. Many times materials have carriers in them to help dispensability. For example, silicone oil being used as in most gap fillers. High-pressure systems tend to dewater the fillers like a filter press in areas where line ID is reduced or flow is restricted. You can see this clearly in Figure 1. Here, continuous loading of the material under pressure separates the liquid and solid material components. Due to their higher flowability and smaller particle size, liquid components are thereby pushed past deposits, while fillers continue to deposit. This causes the material to separate like oil and water, where the oil will be floating on top, as in silicone-based gap fillers. The result? The homogeneous mixture has come out of solution and is now separated, leading to changes in dispense rate. Low viscosity constituents can escape through a narrow gap at contact surfaces where solid components tend to increase in concentration. This results in silting up of moving parts, such as valves, lines, etc. You can see evidence of this firsthand when the silicone bleeds out onto paper. Moreover, thermal cycling of the product leads to cracking when the silicone base is forced out of the solution. The result is dry slugs of filler that can lead to catastrophic failure. Scheugenpflug recommends that when dispensing filled materials, dispensing systems be equipped with a pressure shutoff. In this way, during breaks in production, the operator can activate the pressure switch off to prevent the described sanding down. In addition to high-pressure dispensing systems, another mechanical element that's a common contributor to material quality defects is rotary and eccentric screw pumps. With these pumps, abrasive particles are pressed into the stator, which creates a grinding layer. As material begins to build up, the rotor is ground down, leading to costly teardowns, cleans, and rebuilds, along with increased microsphere breakage. Scheugenpflug conducted an internal test, and after 30 pails of material were ran, excessive wear was exhibited. After 40 pails, breakdown occurred and a costly rebuild. Dual piston pumps, on the other hand, work in conjunction with the metering head to actually push abrasive material in front of itself. The pump comes in contact with the material on only one side, while a barrier fluid on the reverse side prevents abrasive fillers from adhering to the seals. This gives the material preparation system an unsurpassed service life when feeding highly abrasive media. The abrasive particles are washed away from the sealing surface, resulting in less stress on fillers and, consequently, less microsphere breakage. After 250 pails, there was no breakdown of mechanical parts or seals. Material agitation also plays a critical role in maintaining quality when dispensing fluids that utilize fillers. Together with vacuum evacuation, this mixing motion promotes material degassing for low viscosity materials. Agitation facilitates the escaping of entrapped air in the material, which can ultimately be dispensed onto the part, causing costly defects. Overall, the combination of vacuum evacuation and material agitation promotes equal distribution of filling materials throughout the media and is highly recommended for high viscosity materials and certainly for thicker media such as pastes and gels. Compared to degassing without mixing, a particular material being degassed with mixing to the same extent does not require as low a pressure. As a result, the material is not heated to the same extent, which means less expansion of the material during vacuum mixing and a lower likelihood of material decomposition. Recirculation serves a similar role to that of material agitation and vacuum evacuation, particularly in dispensing applications where fillers are used. Circulation of the medium prevents sedimentation and settling of fillers in corners and lines and hoses, which can lead to a number of costly issues, including damage to fillers and microsphere breakage. Recirculation maintains the consistency of the potting material's properties. The degree of agitation and circulation intensity in these systems should be adapted to the material in order to maximize yield and quality. For this reason, operators should consult with an OEM to select equipment and features that meet the unique needs of their particular application. Next up, we have seals and surface finishes. When specifying a dispensing solution, these are critical components to take into consideration. At Scheugenpflug, we see this situation a lot, where seals and surface finishes are not designed to handle the constant bombardment from aggressive fillers and media that's being dispensed. Over time, the material damages the seals and internal surfaces, which inevitably results in the need for more maintenance, costly rebuilds, and excessive downtime, all of which increase system cost of ownership. The solution here is similar to what we've talked about on previous slides, and that is to develop a thorough engineering design specification for all O-rings, seals, and surface coatings, and then engage with a qualified OEM who can deliver a solution that meets those requirements. For example, in applications where cleanliness is critical, medical-grade stainless steel can be spec'd for reservoirs and parts to prevent contamination. Overall, by ensuring compatibility of seals and surface finishes with the media, system owners can ensure uptime by minimizing the chance of premature degradation to internal parts. And now we've come to our last bullet point on the list: temperature. Temperature plays a critical role in reducing filler damage and maintaining overall material quality. Maintaining optimal temperature, however, can be a balancing act. For instance, increasing temperature in a dispensing system improves the dispensability of higher viscosity and two-part materials, such as gels or pastes. However, it also makes it easier for materials to separate, which can lead to costly defects. In many cases, high temperatures will also promote the premature curing when components are mixed. Similarly, for some one-component systems subject to heat curing, the material pot life is changed. The solution for this is to make sure that the optimum temperature is maintained for the material being dispensed. This will ultimately ensure quality and minimize filler damage that may be caused by changes in ambient conditions from day to day or season to season. The better material flow rate and improved quality will ultimately outweigh the shorter material working time to the benefit of the process. Again, this is something that operators can easily achieve by engaging with a qualified dispensing solutions provider. Overall, the most important thing we want listeners to take away from our discussion today is that the adhesive bonding and potting processes have a major impact on the overall cost of part produced in manufacturing operations. Even the slightest deviations or inhomogeneities in the dispensing of potting processes can significantly compromise the quality and service life of components. Ultimately, determining which dispensing solution is the right one for a particular application depends on a number of factors. In addition to the equipment itself, the materials used, the user potting requirements, the potting properties, and the integration of adhesive bonding, dispensing, and potting processes into the production environment all play an important role. One particular solution that can be advantageous in applications that feature highly viscous and/or abrasive material feeding is a vacuum follower plate. The vacuum follower plate is specifically designed for feeding high viscosity potting material from a habak or pail. The plate is made of polypropylene, which guarantees appealing sliding and manufacturing characteristics that aid in the production process. Polypropylene also provides exceptional material compatibility with the most frequently used potting media. The air trapped between the plate and potting material surface is drawn into the plate by a vacuum during docking. This prevents the air from entering the potting material or disturbing the feeding process. It also levels the surface, which facilitates a constant material flow. In the process, the potting material is pushed through the center opening into the feed lines. A fill level measurement system ensures that the drum is emptied completely. Because the plate is a single-use item that is disposed of with the empty pail, the new material is not contaminated with dry material residue. Metering head design is also critical when specifying a dispensing system. For example, in some applications, operators can benefit from utilizing gear pump dispensers, in particular due to their continuous, high-precision material application, as well as their high dispensing speeds, even in the case of complex workpiece geometries. The gear metering pumps provide the needed flexibility for potting different workpieces or for varying material quantities. Dispensing is completely uniform, even at high inlet pressures. In addition, these dispensers provide very careful, low pulsation feeding of shear-sensitive and high-viscosity potting media. Volumetric piston dispensers are an option, particularly in applications using filled or abrasive materials such as 1C or 2C casting resins. Volumetric dispensing offers several advantages. Since the material quantity to be potted is mechanically determined in this case, dispensing accuracy does not depend on the temperature, material feed pressure, or viscosity of the casting resin. This is not the case when it comes to other dispensing methods, such as dispensing by determining mass or by measuring time. Moreover, volumetric piston dispensers are available in different sizes and models and can therefore be adapted precisely to the particular potting task. Overall, when specifying a dispensing system for a given application, it is important for operators to understand that it's not a matter of one size fits all, but rather which solution is optimal given the unique requirements of the user and the process. To fully understand the dispensability of your material, manufacturers should consider getting a lab test done. These tests greatly assist in setting expectations and enable operators to zero in on the specific type of equipment needed to flow correctly and maximize yield. The test can usually be conducted in a single day and is an invaluable step in reducing overall dispensing costs. In the end, to fully understand what your dispensing process is capable of, you really need a dispensing engineer to evaluate it. At Scheugenpflug, we offer a free evaluation, which usually requires a 30-minute discussion over the phone. Our sales team are all engineers and are technically trained in dispensing. We can help you evaluate your existing system to look for opportunities for improvement and ensure that the solution you use provides the most value over its useful life.